This video was almost a victory lap for our custom Unity compositor, an extra rendering path that drew the UI into a full-screen texture, then blended it into Unity's camera. Our Photoshop layers had looked wrong. This path matched them within one value out of 255. The fix worked. Then, just before recording this episode, we tested the option we had dismissed, switching the project to Gamma. The artwork still looked right. Most screens could render directly. Gamma solved the color, but removing the now unnecessary always-on compositor exposed three other dependencies. Pillar boxing, the black sidebars that protect our fixed 16:9 UI on wider displays, had been coupled to it. The region map screen lost its purple bloom glow, and our custom tools for recording promotional material still needed a render texture. Each needed its own, smaller solution. We were right about the pixels. We were wrong about the constraint that shaped the solution. This is how a correct fix became a smaller architecture. The mismatch was visible, but screenshots were not enough to justify a rendering system. So we built a repeatable Photoshop to Unity calibration. The fixture is a small Photoshop document with 6 simple layers, all using the standard normal blend mode, opaque and translucent colors, a gradient, and an anti-aliased edge. We exported the approved flattened result and the same layers as separate PNGs. Unity rebuilt the stack, and an automated comparison checked every RGB channel against the reference. That controlled reconstruction and pixel comparison is what I mean by calibration. In a linear color space project, the same PNGs and opacities produced a visibly different result. We could not flatten the production screens because their backgrounds, characters, shadows, frames, and overlays change independently at runtime. So the original investigation began with a fair question. Why can two sensible applications blend identical transparent artwork into visibly different images? The answer is easier to see with one gray pixel than with an entire game screen. Image files store brightness on a scale designed around human vision. A stored value of 128 looks roughly halfway between black and white. But after that value is translated into linear light, it is only about 21%, not 50%. With the settings used by our Photoshop documents, Photoshop blends the stored image values directly. Unity in linear mode first translates them into linear values, blends there, and translates the result back for display. The opacity formula has not changed. The colors have not changed. Different numbers enter the formula, so the midpoint changes. Put 50% black over stored gray 128, and document space blending produces 64. Linear blending displays much closer to 92. Neither application is broken. Linear blending is appropriate for physically meaningful lighting. Photoshop's document space result was simply the art direction we had already approved. The useful question was not which application was right, it was which set of numbers our UI needed to blend. Our first workaround adjusted texture alpha on the CPU. It helped a narrow case, mostly black transparent artwork, but it could not understand the other layers a pixel would eventually meet. Correcting individual ingredients was the wrong level for a problem created when the ingredients were mixed. The stronger solution controlled the mixing stage. Unity provides a panel settings option called Force Gamma Rendering for UI Toolkit in a linear project. Unity documents it as part of an off-screen texture and custom compositing workflow. We connected that supported behavior to the universal render pipeline. The UI layers blended together in the off-screen target. We then combined the completed UI with the linear camera image before post-processing. This also let high dynamic range UI pixels reach Unity's bloom effect, which spreads a glow around bright pixels. We ran the 6-layer calibration fixture through that path, and it reproduced the tested Photoshop layers within one value out of 255. That was legitimate engineering, not fake color science. If a project must remain linear while a layered UI region must preserve document space blending, this remains a valid conditional design. The mistake came earlier. We had never proved that our project actually had to remain linear. In the original story, switching the whole project to Gamma appeared only as a tempting answer to reject. We said it could affect materials, shaders, blending, lighting, and effects, which is true. Then we quietly promoted that risk into a requirement. Leave the project-wide color setting unchanged. But Rootwoven began as a UI-heavy, mostly two-dimensional game. Linear was the existing project configuration, not a decision backed by a list of visual systems that depended on physically correct lighting. We had treated that existing setting as immovable because changing it sounded dangerous. The right response was not to assume Gamma would be safe. It was to make a branch, switch it, and inspect the real game. The calibration that had made the compositor defensible also gave us the fixture and comparisons needed to judge that experiment without guessing. So we stopped debating the checkbox in theory and tried it. The first result was almost anticlimactic. In the Gamma project, we ran the same 6-layer calibration with our custom compositor disabled. Unity's direct UI result matched the Photoshop reference within one value out of 255. Separate visual inspection showed that the production screens kept the appearance we had already accepted. We inspected the room, dialogue, world map, menus, highlights, and layered transitions. We did not discover a hidden lighting system whose look depended on the linear setting. For this game, Gamma was compatible with the artwork and rendering we actually had. That answers one question only. Can normal UI render directly in this project without losing the approved colors? Yes. It does not mean Gamma is universally better. A lighting-heavy three-dimensional game, physically based materials, or future effects may make linear the right trade-off. If Rootwoven grows in that direction, we will need to revisit the decision. Project color space is an architectural choice, not a cleanup checkbox. And color was not the only job our compositor had accumulated. When we removed the always-on compositor, one accidental dependency was our fixed presentation. Rootwoven uses a pixel-perfect 1920 by 1080 stage because that is simpler than building and testing responsive layouts for every aspect ratio. On wider displays, black sidebars, pillar boxing, keep it centered. The old compositor had owned those bars. The region map screen lost its purple glow, while our custom editor recorders for trailers and other promotional material still needed a stable UI texture. But neither job required every screen to use a full-screen, high dynamic range texture every frame. We restored the fixed 16 by 9 presentation independently. One system centers the UI, while a matching camera viewport keeps the game inside the same rectangle. Pointer input in the bars is rejected. For promotional recording, our editor tools request a render texture for one capture, then release it on success, failure, cancellation, or shutdown. For bloom to spread from the highlighted icon into the surrounding map, Unity must combine the UI with the camera image before post-processing. The region map screen therefore enables bloom and requests the high dynamic range compositor only while it is open. The setting solved color. Separating these responsibilities solved the architecture. The final architecture has 3 explicit paths. Normal screens draw UI toolkit directly to the display. There is no intermediate UI texture, and no extra full-screen composite pass. The region map allocates one floating point UI texture before the view appears. Unity combines that texture with the camera image before post-processing, allowing bloom to create the halo. The texture stays stable for the whole view, so hovering never switches rendering paths or moves the UI. Leaving disables bloom and releases the session. If no recorder shares it, the texture is destroyed and direct UI resumes. Our promotional recorders use their own temporary capture session. They request the texture at the recording resolution, keep it through warm-up and every capture pass, then release it. If the region map is also using the compositor, its session stays alive. Separately, the fixed design stage and matching camera viewport preserve the 16 by 9 presentation whether a compositor exists or not. On wider displays, they leave the pillar box bars shown earlier. Each subsystem now states why it exists, who activates it, and when its cost ends. The calibration was not wasted. It identified blend space as the cause, validated our linear project bridge within its boundary, and supplied a stable reference for the gamma experiment. Evidence built to defend code let us remove most of its runtime use. At 1920 by 1080, the old floating point UI texture contains roughly 16 megabytes of pixel data before driver-specific overhead. Normal screens no longer keep that allocation alive, and they no longer perform the additional full-screen texture sample and blend every frame. That should reduce memory traffic, especially on mobile and integrated graphics, but we have not measured a frame rate or battery improvement. The architectural claim is narrower. Normal screens use less GPU memory and submit less full-screen rendering work. The region map still allocates and composites its temporary UI texture and runs the bloom effect while open. Promotional recorders incur their temporary capture cost only while recording. The uncomfortable conclusion was not that the old compositor was foolish. It solved a real, measured problem, used a Unity-supported technique, and remains useful when a linear project contains layered UI that must preserve Photoshop's blend result. Our mistake was building around a condition we had not verified. In this project, Gamma preserves the authored UI directly. The fixed 16:9 presentation needs no compositor. Promotional recorders request a temporary compositor only during capture. The region map screen requests that compositor only while its purple bloom effect is active. Once those facts were separated, the always-running path had no job left. We kept the approved colors, the fixed presentation, the capture machinery, and the glow. What changed was the scope of the expensive work. The reusable lesson is not, switch every Unity project to Gamma, and it is not, custom rendering is bad. Before defending a complicated solution, name the constraint that makes it necessary and test that constraint against the real product. Then give each remaining requirement its own owner and lifetime. A working solution can still be the wrong-sized solution. The best thing the calibration gave us was trustworthy pixels. Once we had those, we could simplify everything around them.